Good afternoon, everyone. I just wanted to make a quick video to touch on what we will be talking about for these last 3 weeks of the course. We are going to be talking about heat. That is in chapter 12 of your book, so make sure and check that out for more information. Of course, if you look on Blackboard, there is a slideshow. I think it's called Intro to Heat or something. There's a slideshow called Latent Heat, and I now just added a small sheet to Blackboard that's called the Laws of Thermodynamics, because that is one of the first things you'll want to know once we start talking about heat are the 4 laws of thermodynamics, and we'll be utilizing 1, 2, and the 0th law, skipping over the 3rd one because it doesn't necessarily apply for what we're talking about. However, please be aware that there are 4 laws of thermodynamics. And, of course, the lower the number, the more intrinsic it is. But the 0th law is the most intrinsic, but was stated last. So, but check that paper out. And, of course, you can always look for more information in Chapter 12 of your text. I'm just going to very quickly go over a few things that are in the slideshow, the Intro to Heat slideshow. And of course I want to make a larger video over the weekend that has more things worked out. I plan on also, of course, putting all the hints and tips for the homework problems online sometimes next week as well. But we are almost done. And remember, one more thing, like I said in one of the announcements, is that you don't have to take the final in this class. I think we'll be all right without it, but of course it is an option. I would only recommend it if your grade's like, I don't know, an 89 and you want to get that A, or it's a 79 and you want to get that B or something like that. But of course that's your choice. We can talk more about that later. But for now, let me just point out a few things in this slide show that I wanted to talk about. Slide number 3 says, are heat and temperature the same thing? And of course I'm sure you notice that the answer is no. Heat is one of those very ill-defined terms. A lot of times when people talk about heat, they're talking about the amount of thermal energy in an object, but sometimes layman terms, just talking to regular people, for heat you're actually talking about the temperature, but specifically heat and temperature are not the same thing. So really quickly, I want to define something called thermal energy. All of this that we're talking about is going to be thermal energy. Thermal energy represented by the letter Q. Yes, Q. Thermal energy is the total amount of internal energy in an object. So the thermal energy is the sum of the energy that makes up the object. Basically, if you separated an object into all of its molecules and took how much energy each one of those molecules had and then added them all together, that would be the thermal energy of an object. Temperature, however, temperature is a measure of the average energy of all of the particles that make up an object. Temperature is a measure of the average energy of all of the particles or pieces that make up an object. So for instance, if we took that same object and separated it into all of its parts and each little particle had a certain amount of energy, well, we would take that one and add it to the next one and add it to the next one, but then we would take the average of all of those, and that would be a temperature. The term heat itself specifically means the transfer of thermal energy. Heat specifically means the transfer of thermal energy, but that's not usually how we use it in day-to-day life. So those are 3 different definitions, and they can get kind of muddied based on how we use it and how it's used scientifically, but just be aware of the differences of those words. Before I go on to the next slide, I do want to talk briefly about the laws of thermodynamics, or at least the first law. what you'll notice about the first law of thermodynamics, the first law of thermodynamics is actually the law of conservation of energy. Hey, we already know that, so that's pretty cool. The first law says that energy can neither be created nor can it be destroyed. Also, part of the first law of thermodynamics is the work-energy theorem. That's part of it as well. So I just wanted to go ahead and point that out really quickly because I may often refer to the first law and you'll be like, hey, excuse me, what is he talking about? But yeah, so there's that. The next few slides of the slideshow just talk about temperature scales, but one I found that I actually have out of order. Slide number 5, it does mention that we're going to be talking about another type of energy, and that is thermal energy, or sometimes called heat energy. So just be aware that thermal energy, Q, is another type of energy, just like kinetic energy, just like potential energy. And remember, since energy can neither be created nor can it be destroyed, we can always change between those forms of energy somehow. We'll figure out how later. There's a temperature scale there. In this class, most often we're going to be using the Celsius scale or centigrade. But please note that in astronomy they often use the Kelvin scale. We use Fahrenheit in the US, and I have no idea why. Fahrenheit is more based on what humans can bear. The higher the temperature is, the more unbearable it is for you. Water freezes at 32 degrees and boils at 212 degrees Fahrenheit. Cool, right? But Fahrenheit, it's not really... It seems arbitrary to me. Now remember, temperature is a measure of the average energy of particles that make up an object, and the Fahrenheit is just a scale used to measure that. But I prefer the Celsius or centigrade scale because that standardizes temperature using water as a reference. And of course, using water as a reference, water is a physical object, and using its freezing point or boiling point as references helps give a more physical part to what the temperature scale actually means. So we'll use the Celsius scale. You can see there on the slideshow how Celsius relates to Fahrenheit. And then there's a Kelvin scale, which, like I said, we often use in astronomy. And when I write papers, like scientific papers, I'll use the Kelvin scale. The benefit of the Kelvin scale is it's the same scaling as Celsius, thumbs up, but it just eliminates any of the negative values. So Kelvin is pretty beneficial because then there will be no negative numbers. Next few slides, like I said, just talking about scaling. And then you get a page that starts talking about heat, and it mentions calories. Now, calories is actually a measure of the heat, the amount of energy required to raise 1 gram of water 1 degree Celsius. In my honest opinion, I don't care for calorie as a unit because it's not based off of base units. However, looking at this slide, you can see that the term calorie with a little c is a certain amount of energy. And 1 calorie, lowercase c, is equal to 4.19 joules of energy. And of course, joules is a base unit. So you see how calories relates to that base unit. Now, if you look on the back of your food product, you'll notice that it says such and such calories. That is capital C calories. And confusing enough, the capital C calorie is equal to 1,000 energy or lowercase c calories. So it's some unit craziness, which is why I hardly ever use calories as a measurement unless I'm reporting to a group that cares about how it relates to food you eat, which is not something I do very often. So, but I do want you to be aware of it, so check out slide number 8 for that. On the next few slides, it asks you how much heat is equivalent to 75 joules of work. And of course, you can just use the ratio of 1 calorie equals 4.19 joules to figure that one out. I'm not going to go into great detail on that. The next one says a fuel yields 1.15 times 10 to the fourth calories per gram when burned. Again, you can use a ratio of 4.19 joules per calorie to find this. This is basically just practice for warming up to talking about what we really want to get into, and also to remind you that yes, calories are actually energy. Next is a slide that talks about transferring heat. And it talks about how, heat is the transfer of thermal energy. I don't really think I need to talk too much about that. What I want to get into is start talking about the specific heats and what the equation that we'll be working with most of the time is. You can see it on slide 18 that says Q equals MC delta T. So that equation is, it says Q equals MC delta T, but what Q equals MC delta T means is that the change in energy is equal to the mass of an object times the object's specific heat times the change in temperature. But I don't want to get too much into that today. This is just going to be a short 12-minute video. I'll give you some time to look around and play around and read on stuff, and I'll be making a larger video talking about what we're going to be doing with this thermal energy later, maybe over the weekend or Monday. But that's it for now. Thank you very much. We'll have a nice day.